inviting me in this nice place. It's great to be here after 2 years. And giving me the opportunity to talk about my work. So there is nothing about hydrodynamics in my talk. Everything is at 0 temperature, so it's very simple physics if you want. But yeah, so I'm coming from a slightly different community. Well, originally I was working on condensed matter problems, and then I switched to more high energy applications. But I am trying to keep up to date with what happens in my original community, so I'm happy to be here and learn about progress in this field. So there is some common mathematical structure between what the problems that I am trying to solve and some this community are solving. So the common structure is integrability, so two-dimensional integrable field theories. So I will try to make some connection. I think the closest connection to what was said here is with the work of Tomohiro and Kazuya, the talk that you heard a few days ago about Fredholm determinants. So, this is a work that we finished recently with my student Gabriele Fundes, my former student Gwenaël Ferrando, my collaborator Shota Komatsu, who is in CERN, and some previous work with Ivan Kostov and Valentina Petkova. So it's about correlation functions in integrable supersymmetric gauge theories. So the motivation to study this problem is to try to find the description and strong coupling of 4D gauge theories. Think about QCD. But in order to understand this this theory using, for example, holography, we prefer to look at a more symmetric of QCD, which is called n=4 supersymmetric Young-Mills theory. So the degrees of freedom are almost the same, but this theory is more symmetric. It's conformally invariant in 4 dimensions. The drawback is that there is no confinement, but still we can, thanks to the fact that this theory is exactly dual to a string theory, one can understand precisely on this example how holography works. And the remarkable thing about this theory is that in the limit of a large number of colors, or the large size of the gauge group, this theory is integrable. So this holography correspondence, we can understand it precisely mathematically, in mathematical sense, using integrability. So the mapping that I am going to use is between operators in this theory, n=4 super Young-Mills theory, two integrable spin chains. So we are looking at some fundamental fields. I will explain a little bit better what these fields are in the next slides. But we are taking these matrices. These fields are n by n matrices. We take the product at a particular point in space-time, 4-dimensional space-time, and then we take the trace over the gauge group. So there is a precise mapping between these kind of operators and an integrable spin chain. And the way that these operators transform under dilations is mapped to the action of an integrable spin model on this spin state. So what I'm going to concentrate in particular is how to compute the correlation functions in these theories. and in particular how to expand them in terms of non-local form factors. And in practice, what this is serving to is one motivation is to replace computation of Feynman diagrams by interpreting them in terms of contribution of quasi-particles in an integrable 2D theory.
Is there also correspondence at the level of dynamics, or is it only at the level of the single leg? Is it like if I did dynamics in that super spin chain, would that correspond to anything?
Yeah, that's a good question. People were not yet interested about this because computing, well, there is also a relation with computation of amplitudes, and this is something that people are, I mean, from the practical point of view, it's an important question and then unsolved. So yeah, but yeah, that's a good question.
Isn't it, if I remember correctly, the dilation operator becomes the Hamiltonian of the chain?
Yes.
Yeah. So essentially, dynamics would be a scaling.
Yeah.
Which is an interesting question.
Yeah, of course.
Okay, I have a naive question.
Yes.
So integrability in these systems, I guess, comes with some asterisk or disclaimer because it's about kind of low energy states. If you look at states at above a high enough energy that scales with it, and then you have black holes, thermalization, and so on. So they're actually not integrable when you consider the full spectrum.
So I'm looking at zero temperature. I'm looking at all the states.
Yeah. So you take n to infinity first before the thermodynamic limit.
There is a precise mapping between every state of, I mean, every operator in this gauge theory and any state in the spin chain. And any state in the string theory in this curved.
But if n not curly n the other
NC
were huge but finite, there were at some point you'd start to see states that are that thermalize as per the IPhT.
In the string theory, well, you start to see a different. You start to see different topologies of the string. So yeah, this is a little bit out of the reach of integrability. But in principle, the mapping is also the mapping between n equals 4 super Young-Mills and the string theory is also should be valid also in this case. But it's less accessible to integrability techniques. There is the localization techniques works for some observables beyond the planar limit. So for finite NC, so that's something that has to be explored, of course. Yeah, but I will mainly concentrate on what we can say about the theory through integrability, so the planar limit. But yeah, there are things that are done for the 1/n² corrections. Yeah, so the plan of the talk will be a lightning review of ADS-CFT integrable spin chain, then how to compute, what is the technology to compute the correlation functions in this n equals 4 super Young-Mills theory. I will mention as a particular type of 4-point function which can be written as a Fredholm determinant. And then I will switch to a twisted version of this theory, which was less studied by integrability, but was studied with supersymmetric localization. And in fact, the work we have done was to relate the results obtained with localization, matrix model techniques from in this theory with what was done previously for the non-twisted theory. Okay, so to remind the ingredients of this integrable spin chain, so you can think about thought it as a supersymmetric generalization of isotropic Heisenberg spin chain. So you have more degrees of freedom, and you have higher symmetry. The model is long range, and the range of the interaction is controlled by by the coupling constant of the theory, which is a combination of the Yang-Mills coupling constant and the number of colors. And when I'm talking about planar limit, will be the limit where this number goes to infinity. This one goes to 0, such that the coupling constant is finite. And as I was saying, the theory is conformal, so this parameter is correspond to a marginal kind of marginal, exactly marginal perturbation of the theory. So this will be a parameter of my spin chain. The states, so the states of the spin chain are in one-to-one correspondence with the fundamental fields of the theory. So I didn't write down the Lagrangian for the theory, but yeah, it's a gauge theory. You have the gauge field, a connection, a mu, and in addition, you have 6 copies of bosons and 4 copies of fermions, which are related with gauge field through some by the action of supersymmetry. So the whole symmetry of the theory is the theory which rotates the bosons among each other. So this is SO6 or it's isomorphic with SO4. So SO6 permutes these 6 fields. SU4 permutes these 4 fields here. And also the supersymmetric generators send bosons to fermions. So the whole symmetry of the model is given by superly algebra, which is PSU 2,2/4. So this bosonic symmetry is a sub algebra of this bigger group. So when you are looking at the duality with the string theory, you see that the symmetry is also the isometry of the sphere times the hyperbolic version of the sphere in 5 dimension, the ADS space. So if you want to understand the connection to isotropic Heisenberg, you can concentrate on combinations of these bosonic fields here. So you can make some complex combinations of them. So let's say that Z is a complex combination of phi1 and phi2. I call X phi3 plus I phi4. And these 2 states, I can consider them as spin up and spin down for some Heisenberg spin chain. So these two states form a SU2 subsector of this group here. And I will use in the following this representation here. So for my spin chain, I have a vacuum, like the spin up everywhere state. And this will be in one-to-one correspondence with trace of Z to the L. So this is the vacuum of the Heisenberg model, and for my theory, this is a particular state which is protected by supersymmetry, and which I will call BPS state. So all the states protected by the symmetry, whose scaling dimension are not deformed when I switch on the interaction. They will be called BPS states. So when you are doing your Bethe-Ansatz study of your spin chain, you choose a vacuum state. This vacuum, this trace Z to the L for a magnetic state, and then you are flipping some spins and you are creating magnons. So here, because the symmetry is so big, the magnons are not just U1 have not just U1 charge like in the usual isotropic Heisenberg SU2 case, but here they carry some symmetry, which is PSU2 times PSU2. So to distinguish them, I will call them left and right, and they will scatter with some scattering matrix that was fixed, written down by Bizart by using supersymmetry constraints. So under this mapping, you certainly know the Sutherland type solution of the spin chains. Also, they appear in the study of quenches when you are making excitations close to the ferromagnetic spin chain. So they were also called in the condensed matter literature giant Magnum solutions. These are mapped to rotating string solutions in string theory. And in terms of the string sigma model, they correspond to what are called finite gap solutions. They have semi-classical limits, well-defined semi-classical limits. So you can think about the string sigma model as, of course, you know the description of spin chains in terms of sigma models. So if you take this spin chain here, you try to describe it on large scales with some sigma model, you will get the string sigma model that was written by Metzais and Zeitlin more than 20 years ago. And the last important part of the story is to compute finite size corrections, because for the spin chains, because we are interested in operators which can have any size here, like 2, 3, and so these spin chains have finite size corrections, and they are very important in practice to compute. So they were obtained via refinement of the TBA approach, and they are now known as a quantum spectral curve. So that writing down this set of difference equations was the big achievement of this integrability program. And in principle, they define exactly the solution for this anomalous dimensions or energies of the spin chain in terms of the coupling constant. So there is a extensive, there are a set of extensive checks of the dimensions of the operators compared with perturbative computations from the gauge theories, perturbative computation from string theory, so everything matches perfectly. So that's a very fine verification of the ADS-CFT conjecture in the first place. So let me now try to explain the data for the correlation functions. So I was saying that we are looking first at two-point correlation functions from the point of view of this 4D conformally invariant theory. So of course, in conformal field theory, the two-point function is fixed by conformal invariance, and the only thing that we have to compute is this anomalous dimension or spin chain energy. So this problem can be considered as solved. And then if we want to go further and compute correlation functions with more points, the first non-trivial case is the one of the three-point function. So you can imagine this through the duality with strings. You can imagine it as a interaction of three strings. Also superposition of different spin chains in the language of spin chains. And this, the only thing that is not fixed by conformal invariance are these structure constants here. So these are the type of objects that I'm trying to compute in the following. In principle, in a conformal field theory, it's enough to have this the three-point function computed exactly, and then by OPE expansion, in principle you can get the other higher point function. But I will explain that there is a more fundamental object that we can building block of the correlation function, which so from which the higher point functions can be computed. So the idea is to that we can after a lot of trials and errors, what really worked to compute the three-point function was to take this object and cut it in two surfaces, two separate surfaces. So if you cut a pair of pants, you will get two hexagons. So the three-point function is determined, of course, by what operators you are inserting here. So it's going to be determined by the rapidities that you insert on each of these curves of the pants. So when you are cutting this the pants into hexagons, you're going to split the collection of rapidities here. For example, U1 will be distributed in the two hexagons. So the result, if you are ignoring the finite size correction, this is what this type of structure constant without the finite size correction is called asymptotic. So that will be just given in terms of some superposition of some product of contribution of these two hexagons with different distribution of rapidities on them, all the possible distributions. And then you have to glue these two hexagons with some gluing factors, which depend on the length. So imagine that you are splitting this object into three. So you will get the distribution of L1, L2, L3 into three bridges, L12, L23, L31. That will be the length of the pieces that you have cut on each side of the of this hexagon. So this Lij will be the length of the bridges that are associated with these three cuts here. So this is essentially the procedure to compute the three-point function. You will get some finite size corrections by inserting on each of these cuts here the composition of identity. So you will have to sum over all the virtual particles that can circulate inside this the space here. So but if the bridges here, if the lengths are large, L1, L2, L3, you can forget about the virtual excitation that flow inside this surface. So to explain a little bit, yes.
So this was a bit quick. So on the previous slide, so the previous picture, this was just conformal field theory, or was this specific to the spin chain mapping?
This is, in fact, this will have an equivalent in string theory. Imagine that this is a sphere with 3 insertions, and then you are splitting this sphere with 3 insertions into 2 triangles. So you are doing some triangulation of the sphere. So this is, I think it goes under the name of Teichmuller theory. You are splitting a surface into triangles, and then you are patching this. So it's more like a string theory procedure. This cutting, splitting of surfaces and gluing surgery of surfaces in string theory.
And what's a virtual particle in this context?
So okay, probably this in this. Imagine now that I don't have this hexagon here. The hexagon has some curvature defect. But let's compare a local form factor with a local form factor. So imagine that you have a regular integrable 2D field theory. So you have you can interpret form factor, so which is a product between vacuum operator and the state with, let's say, 2 magnons, like this. So you have the vacuum here, you have the 2 magnons here, and here you propagate some surface. So you can, in principle, you can. These are slices of equal time, but these are slices with equal space. So you can imagine particles that you send from this time-like slice. You can send them here by what is called the mirror transformation. So in the integrable relativistic field theories, the rapidity is called not u but theta, and the relation between p and e are given by this parametrization with hyperbolic functions. So if you are sending theta to theta plus I pi over 2, you see that you are exchanging energy and momentum. So you are doing this Wick rotation. So this is what a virtual particle is for me. A particle that I took from this physical slice here, and I send it on this slice doing this mirror transformation. Is it intuitive? So the thing is that our spin chain is a bit special. Is not has also something like it's not relativistically invariant, but this procedure here is well defined. So we can do now. If I'm coming back to my non-local form factor. So these hexagons, if you are looking, so I want to have straight 90 degrees angles here. So I have 90-degree angle here. So if I want to accommodate for my straight angles, I have to introduce a defect in the middle. So the object is kind of junction of 3 open spin chains, one here, one here, one here. And this kind of form factors, non-local form factors, were studied by Benjamin and his collaborators. They had an integer number of 2 pi as a defect curvature for the form factors, but yeah, you can put any fractional number of 2 pi, and you compute this this object. So that was that was obtained. So for this hexagons here, people were smart enough to be able to find using the form factor bootstrap. They were able to find the solution for this for the form factor axioms for this theory, which is given in terms of, so I was saying that each of these magnons carries some degrees of freedom, some PSU to 2 degrees of freedom, left and right ones. So the amplitude for these hexagon weights are given by some prefactor, which is called hexagon amplitude or dynamical part, and then some matrix part, which is essentially given in terms of the matrix Bizart's scattering matrix for the spin chain. So are there any questions up to now? If not, yeah. So this was how to obtain the building block of the correlation functions. Now you can do so. You can, from this building block, you can compute any number of correlation function with any number of insertions. So the suggestion how to do this was made by Fleury and Komatsu, and also another group simultaneously. So they proposed in conformal field theory, what is natural is to take what is called the OPE expansion. Let's say cut this 4-point function into two pans by cutting here in the middle. But in fact, it's much more efficient to just to do this kind of decomposition where you're using a kind of triangulation of the sphere with 4 insertions. So this suggestion proved to be very efficient, and this is something that you can use for any number of insertions. So as I was mentioning previously, when you want to sew back these form factors here along these seams, you have to insert a resolution of identity on each of these seams. So technically, the computation can be quite involved. It is as involved as it is when you are doing this form factor decomposition in local correlators in an integrable 2D theory. So it can be, since you are working with interacting theories, not purely fermionic theories, this can be rather complicated to achieve. But there is an example where it was possible to do this explicitly. So this is the case of the octagon that I will mention below. One of the complications of this procedure is then when you are gluing 2 times like this, you are reconstituting a leg of the pants. The procedure is a little bit ill-defined, and you'll get divergences in this channel. So these divergences have a very well identified physical meaning, and they are related to the TBA description of one of the operators. But this recovering this TBA from the form factor was not achieved. The important steps were done in this paper here 3 years ago. So in order to avoid the problems with these divergences, one solution is to take here a vacuum state. You just insert vacuum. So you don't have, there are no divergences. So you cannot do this for the 3-point function because you will get, by supersymmetry, you will get something that has no correction is in G. It's just something which is equal to the value to the factor of the theory. So it's not very interesting from the point of view of holography, let's say. But so you can do this if you insert. I mean, you can consider a 4-point function with just vacuum insertions. So this is what we have studied with Ivan 6 years ago, with Ivan and Valentina Petkova.
Can I ask you?
Yes.
So you see there are divergences, but the object itself should be finite, right? So what is the interpretation of divergences?
So no, the divergences are. So they are a little bit like the divergences of the diagonal form factors in infinite volume, because in some sense these legs here are on infinite volume because they are inserted on the boundary of the on the R4 R3 which is on the boundary of the ADS space. They are also related to the divergences when you are doing renormalization of your fields.
Yeah, but so here like they should be all where they kind of renormalize appropriately.
Yeah, so we know what they should be, but to get this for resumming Lucier corrections, this is I mean this procedure is not well understood. I will come.
The volume regularization then would actually work like it does.
Yeah, but to resum this whole series, this is not easy to do systematically. But I will come to this later. So for this special 4-point function, so you can insert now 4 vacua state on the sphere, and in fact, by conformal invariance. This will only depend on 2 cross ratios that are given in terms of the position of the insertion by these formulas. So Coronado suggested to consider a particular version of this 4-point function where the length of these 4 operators is very large, goes to infinity. So then the length of these 4 bridges here, if you engineer it properly, it will separate. These bridges will prevent virtual particles jumping from one side to the other. So your sphere is effectively separated into 2 disks. So when you are doing this, hexagon decomposition, you are getting 2 octagons, which are obtained from 4 hexagons by gluing the hexagons 2 by 2, by summing over all the virtual particles that are situated on this seam of on this gluing cut, gluing on this cut. So the 4-point function is written in terms of trivial prefactor, and then the square of this object, which I call octagon weight. So what we were able to do with Ivan was to compute this sum explicitly and get a Fredholm determinant out of it. So since then, this Fredholm determinant played an important role. So in our field, it was analyzed in different regimes by Belitsky and Korczynski, and also recently resurgent analysis was practiced on this object because it depends on the coupling constant. So at large coupling constant, there is are non-perturbative corrections, so all the theory of resurgent analysis can be applied on it, and also some interplay with integrability between the resurgence and integrability was taking a prominent role. So let me. Yes.
So Fredholm determinant appears as Fredholm expansion.
Yeah. So let me explain how what is the idea behind this. So I have my octagon here. Now I can put some. I can introduce an extra parameter, which will be the length of the bridge between the two hexagons, which will be finite. So it's an extra integer parameter that we can introduce into our problem. So the object that I call octagon will be a sum over a number of virtual particles that are exchanged between these two hexagons. So they are represented here by the red lines. So I have a multiple integral with n variables, and then some simple kinematical factor which contains the cross ratios and also some information about the charges the operators that I feed in. So this now Tomohiro will probably be interested by this multiple integral. So you see I have integral over rapidity, sum over the bound state index, because these magnons have can make bound states. There is some one particle measure that contains I don't know, information about cross ratios, the energy of the particles that cross here. Sorry, the L here is the same as the curly L here, but yeah, copying formulas from different sources can introduce some mismatch of notation. So yeah, so this one particle measure contains information about my kinematics, and then there is this factor here, which is two-particle interaction, which comes from the hexagon form factors, the way that the excitation interact with each other. So in this particular case, it's a product of 4 factors with some the rapidity u enters via a variable which is called Zhukovsky variable, which is given by this transformation here. So the details are not of so much importance, but what is important is that this two-particle interaction can be written as a Pfaffian. There are other examples of correlation functions where this is just it can be written as a Cauchy determinant in some other cases. For example, if you go at g to infinity, this object here becomes just a Cauchy determinant. So you see that if you are writing your integral as something one particle and then some Cauchy determinant, you can write the whole integral as a Cauchy determinant of individual integrals. So this will lead you to the Fredholm determinant formula when you are summing over all all numbers of excitations here. So this is very robust. This is very this is a phenomenon that we see in all the correlation functions we are studying, and this is also what Tomohiro and Kazuya see in their problem, that the integrals we're manipulating have this determinantal structure. And I think this comes, in your case, you have some scalar product, some Isергin determinant, and this is what that comes into this measure. Okay.
Do you see something like iseregularity determinant here?
In a different but related problem, yeah.
Iseregularity determinant is usually related to this domain or partition function. Right?
Yeah. So
do you think something similar?
Yeah, I can explain more in detail, yeah, that's a particular case. I mean, Isargin determinant is a particular case when G goes to small values, and then we are considering some particular correlation functions. Then our object becomes essentially an Isargin determinant that can be written in terms of this multiple integral representation.
Maybe related to this, almost at the beginning you mentioned that if you focus on some subsector of your problem, it becomes the usual.
Yeah. So that's
this kind of formula remain in this limit?
Yeah. So that was that is in a paper we wrote in 2016 with Ivan Shota and our students from that period. So if you are doing if you are looking at the you forget about virtual corrections. You are doing just taking a non-trivial distribution of roots here, trivial here, trivial here. Then this asymptotic three-point function can be written as a scalar product between off-shell, on-shell beta state that can be written in terms of a domain well-partitioned function and in terms of Isargin determinant. And then if you're writing things, it's possible to write the Isargin determinant in terms of such kind of integral, with this measure being the Cauchy determinant.
Thank you.
Yeah. So if you are then once you have the one particle integrals that enter into play, you can explicitly write these integrals. It's better to go to the Fourier space, and so that we have this transformation here for the rapidity. So this functional form of the dependence of the rapidity will come into this Bessel functions when we are writing our object. So in the end, the octagon will be written as a Fredholm-Pfaffian, but the Fredholm-Pfaffian can be written in terms of a determinant of some kernel here that some infinite dimensional matrix. That's what we call the octagon kernel, which is a Bessel kernel, since it's defined by these Bessel functions here. So this object appears everywhere in ADS-CFT objects, in the sense that these Bessel functions appear everywhere, and the only thing that changes from object to object is this function here. So in our case, this function is given by essentially in terms of z bar, the kinematics of our 4-point function. If you see that if you are making a change of variable here, you also can put all the dependence in the coupling constant in this test function. So this is a bit like Fermi-Dirac distribution. So you can consider G as a kind of temperature in particular limits. So that's the structure. That's the object that I wanted to show you. because I think it also appears in stochastic processes and in other spin chain computations. So it also appears in IDS-CFT in other places, in n equals 4 super Young Mills in other places. But also it appeared in a different gauge theory, which is a kind of daughter of this n equals 4 super Young Mills. So quiver n equals 2 super Young Mills theory. I will try to go a little bit faster to be able to explain what I want to do. So essentially, the n equals 2 quiver theory is obtained by n equals 4 Young Mills by twisting the SO6 part with some twist, zk twist. Omega is the kth root of unity. So essentially, all the field content is the same as in for n equals 4 super Young Mills, but just there is a definite action of this twist. So Z and Z bar operators are invariant with respect to twisting, and the others are not invariant. The supersymmetry is reduced from PSU22 to something less. This, so you're going from n equals 4 to n equals 2. And it's expected to be integrable, so there was some work done in, well, I think I started a little bit later, so yeah, so there are results from, well, it's expected to be integrable, but no, not so many results were obtained recently, but there are results from supersymmetric localizations via matrix model that was obtained by Pestun. And the results were the results obtained by localization concern what is called the BPS or vacuum sector, where you are taking now this Z to the L operators, and you can insert a twist, arbitrary powers of twist here with alpha going from 1 to K. The dimensions are still protected by supersymmetry, so there are no corrections, but the 2-point functions, so if you insert no twist, they have the same value as in the parent theory. But if you insert a twist in the theory that you can represent by this inserting this twist on in the worldsheet, then you get some an expression which contains this octagon kernel that we have seen previously, with some particular value of the parameters that you have seen recently, and the dependence on the value of the twist is given by this simple function here. So that was the 2-point function. Also, people obtained the 3-point function by using this localization matrix model computation. So now the 3-point function will be such, I mean, in this context, the 3-point function will have the sum of the length of these two legs will be equal to this leg here. This is what is called the extremal. So the result that was obtained by localization is given again in terms of the octagon kernel, but then there is this strange square root here. So okay, these results look very similar to what we got by integrability, but they were obtained by localization. So the question that we addressed is, can we obtain this from integrability? And the answer is yes. We are doing again our game of splitting the 3-point function into hexagons, inserting the twists on when we are gluing again the 3-point functions, the hexagons into 3-point function, and we sum over all the possible insertions of virtual particles on these mirror sides. So we can trace back different contribution in this 3-point structure constant, you see that the result is factorized into 3 factors associated with each of the legs. So there are 3 types of contribution that we can identify. One is very similar to what we were doing previously, summing excitations on the different bridges. But then there are there is contribution from the contact terms. For example, when the rapidities of these two particles on different cuts are coinciding, there are some extra contact terms that are responsible, for example, for the divergences in the case when these states are not the vacuum states. So this would be the bridge, this would be the wrapping, and then there is another strange object that appears when the three different magnons on 3 different sides have the same rapidity, and these look exactly like the bridge contribution, but they have a different origin, so we call them bridge-like. What was the thing that we achieved is how to get these wrapping corrections here, because that was suggested by Benjamin Basso, how to do it by gluing 3-point function into larger structures. So here what we achieved is to glue two 3-point functions into a kind of a closed surface with two holes, and then cut it differently. So essentially, I don't have a lot of time to explain, but we want to cut this structure here into 4 hexagons, and then glue them over these bridges here, and then send the length of these bridges to infinity. So this procedure will give the volume regulator for the 3 legs, and then we get well-defined contributions. So the result of this procedure was an expression for the general wrapping corrections for our object, which is written in terms of some torus partition function of a vertex model build up from the Bizard scattering matrix, and this expression here we were able to check that up to 3 magnons reproduces this the square root the square root here. I'm almost done. Okay, so that was our result. So we are able to put together 2 techniques that were considered as independent. We think we can repeat this kind of procedure on putting the system on a closed surface with higher genus to look at the TBA corrections for more complicated cases. When we have TBA, here we don't really have TBA. The system is in some sense free fermion. And it's possible to do it for higher point functions. They are complicated, but we are looking at the strong coupling regime. Okay, so that's more or less what I wanted to say. Yeah, sorry for the delay. Thank you.